Hello, chemists. This is Miss Placino, and you are watching Screencast 7.1 on intermolecular forces. Today we're going to talk about the attractive forces that hold molecules of a substance together. So the do now is asking you, how often do you think chemists work with a single molecule? Explain your answer. Well, you know the molecules are extraordinarily small, so it's highly unlikely that at any point in time a chemist is working with just one single molecule. We're working with hundreds of thousands of millions of molecules at a time. Often we're working with moles of molecules. So we can't just pay attention to how a molecule behaves all by itself. We have to look at how molecules behave in groups, and that means taking a look at intermolecular forces. You've probably heard the prefix inter before. Like an interstate highway runs between at least two different states. If you're told you need to work on your interpersonal skills, that means that you need to work on how you communicate with other people. When we're talking about intermolecular forces, we're talking about the forces that exist between molecules. It turns out that there are attractive forces that are going to hold molecules of a substance together. Some molecules are going to behave like little magnets and be strongly attracted to one another. Other molecules have a much weaker force of attraction. So today we're going to talk about the different types of intermolecular forces and really the impact that intermolecular forces are going to have on the physical property of boiling point. So what we have here is a picture of molecules that you are hopefully very familiar with by this point in time. We've got water molecules, H2O. So far what we've been studying is the attractive force or the chemical bond that exists between the oxygen and hydrogen atom. We can call these intramolecular forces. Intermolecular forces occur when two different atoms are going to share a pair or multiple pairs of electrons. So these are attractive forces, or bonds are another way to think of them, within an individual molecule. In this lesson, we're going to look at intermolecular forces. I know they sound very similar, but they're actually quite different. Intermolecular forces are talking about the forces of attraction that exist between two different molecules. So in this case, the oxygen atom of our first water molecule and the hydrogen atom of the second water molecule aren't sharing any electrons. They're not bonded together, but they are going to be attracted to one another. If you remember, oxygen has those two lone pairs of electrons. We have a large difference in electronegativity between a hydrogen atom and an oxygen atom. So if we think back to the bonding unit, we know that water is a polar molecule and that the side with the oxygen is going to be slightly negative as electrons are pulled away from the hydrogens and towards the oxygen because oxygen has a higher electronegativity. That means the hydrogen side of the molecule is going to be slightly positive for exactly the same reason. Electron density has been pulled away by the oxygen, leaving the hydrogens as slightly positive. So you can imagine that if you have a slightly positive charge from one hydrogen atom on a water molecule getting close to another water molecule, it's going to be attracted to the slightly negative side of the water molecule. So this hydrogen atom and this oxygen atom are not sharing any electrons. They're just attracted to one another like little magnets because we've got the negative side of one water molecule attracted to the positive side of a neighboring water molecule. And that's all intermolecular forces are. We're going to look at the different types, see how they differ in strength, and see the impact they have on boiling points. First type of intermolecular force I want to talk about are dipole-dipole forces. From your reading, hopefully you know that dipole is just another word for a polar molecule. Something like hydrogen chloride is a polar molecule. We see a large difference in electronegativity between the two atoms that are bonded together. Hydrogen has a low electronegativity. I think it's like 2.1, trying to remember off the top of my head. Chlorine, I think that's about 3.2. So we're talking about like a 1.1 difference in electronegativity. That means the chlorine atom is going to hog those electrons that are being shared between hydrogen and chlorine. And it's going to have a slightly negative charge, as indicated by the delta negative sign, and the hydrogen atoms will have a slightly positive charge as indicated by the delta positive sign. You've got the positive side of one molecule being attracted to the negative side of another molecule. So if you have a bunch of hydrogen chloride atoms, they tend to kind of stick together in a sense because you've got this attractive force. You can think about them behaving as little magnets. In order for dipole-dipole forces to exist, the molecule has to be polar. You need a positive side and a negative side. If you have nonpolar molecules, well, the whole thing doesn't have any sort of unequal charge distribution, so dipole-dipole forces cannot exist. And dipole-dipole is a strong intermolecular attraction. It's going to require energy to pull these HCl molecules away from one another. They are attracted to each other through dipole-dipole attraction. There's a very specific type of dipole-dipole attraction called hydrogen bonding. You can probably deduce that hydrogen bonding involves the hydrogen atom. Water is an example of a molecule that undergoes or experiences hydrogen bonding. This is, again, a very specific type of dipole-dipole attraction. It's going to occur when hydrogen is bonded to a very small, very electronegative atom. More specifically, we're going to see hydrogen bonding most frequently when we're talking about hydrogen bonded to nitrogen, oxygen, or fluorine. The reason that this is a special type of dipole-dipole is because the bond between the hydrogen atom and the hydrogen and the oxygen, or the hydrogen and the fluorine atom is going to be extremely polarized. So nitrogen, oxygen, and fluorine are excellent at pulling electron density towards themselves, so that's going to leave hydrogen very exposed. So we have one very positive side and one very negative side of the molecule, so they're going to stick together with a very strong attractive force. This is, in fact, the strongest intermolecular attraction. So we're going to see hydrogen bonding anytime we've got nitrogen bonded to hydrogen, oxygen bonded to hydrogen, or fluorine bonded to hydrogen. We'll do some examples with that. The last IMF that I want to talk about are London dispersion forces. London dispersion forces are very weak intermolecular attractions between temporary dipoles. We've got this little picture over here on the right-hand side. So we've got nonpolar molecules in this case. And you can imagine with the electrons moving all over the place that it's possible that at some point in time you end up with one atom that happens to have more electrons around it than the other atom. That's going to create a very temporary dipole, where for a brief moment in time, one side of the molecule will be slightly negative, the other side will be slightly positive. If you have a neighboring molecule that's close enough, it could be influenced by this temporary dipole, or this temporary separation of charge, and for another moment we might be able to see kind of the same thing occurring. And just like with permanent dipoles and polar molecules, the positive side of one molecule will be attracted to the negative side of the other molecule. Now, the electrons are in constant motion, so you can also imagine that at some point in time, the electrons kind of distribute themselves evenly again. We're going to lose that temporary attractive force between the two molecules. London dispersion forces are the only attractive force that exists in a nonpolar molecule, and they are extremely weak. It turns out that if you have smaller and smaller atoms or smaller and smaller molecules, you're going to have weaker and weaker dispersion forces. A question that comes up a lot on the Regents exam pertains to diatomic molecules. F2, Cl2, Br2, and I2. The question will usually ask you something to the effect of, why is Cl2 a gas at room temperature but I2 a solid? Well, it all comes down to intermolecular forces. And you probably don't have a periodic table in front of you, but chlorine weighs about 35.5 grams per mole for each atom. Iodine is about 127 or so grams per mole per each atom. So we see a very large molar mass for I2, a relatively speaking smaller molar mass for Cl2, and because we know that smaller molecules or smaller atoms have weaker dispersion forces, the reason we'd see iodine existing as a solid is because it has a much stronger intermolecular force. It's still London dispersion, but because it's larger, it's going to have a stronger dispersion force than Cl2. Okay, so those are our three different types of intermolecular forces. Dipole-dipole, which is strong. Hydrogen bonding, which is a super strong form of dipole-dipole, and London dispersion forces, which are relatively weak. Whenever we go to boil a substance, we have to break intermolecular forces. If you think about it, if you take water and you go to boil it, you're not trying to break the intramolecular force or the covalent bond that exists between a hydrogen and an oxygen atom. You are trying to separate all the water molecules away from each other so that the molecules are free to escape as a gas. Usually, for most compounds, the greater the molar mass, the higher the boiling point is going to be, especially if we're talking about nonpolar molecules that have those very weak London dispersion forces. You might imagine that as the intermolecular force gets stronger and stronger, the boiling point is going to go up, and that is definitely the relationship. Stronger intermolecular forces lead to higher boiling points. At this point in time, it'd be great if you could pause this video, and there's another video linked on the web page about boiling points. So I think it's not even a 2-minute video, but take the time to watch that. At the end of the video you just watched, you were given a graph that looks something very similar to what I've got on the screen right now. It's showing the relationship between the molar mass and boiling point of the group 14 hydrides, which I have in blue, and the group 16 hydrides, which are shown in red. So intermolecular forces play a huge role in this gigantic discrepancy in boiling point between water and methane. If it wasn't for any sort of intermolecular forces, since water and methane have similar molar masses, it would be assumed that they have similar boiling points. But as you can see from this graph, that is definitely not the case. So I'm going to take just a minute and kind of fill out the chart that we have to the left of the graph and answer some questions about this plot. So why don't you pause the video, see if you can draw the Lewis structure for these 8 different molecules. They should be strikingly similar. Also predict the type of intermolecular force you would see. Okay, so I'm going to start with the group 14 hydrides: tin hydride, germanium hydride, silicon hydride, and methane. In all these cases, we have highly symmetrical molecules that are covalently bonded. So for all of these, since they're so symmetrical, they're very likely nonpolar, and if that's the case, the only intermolecular force they can have are the very weak London dispersion forces. Ooh, that first F looks terrible. LDF, LDF. Okay, if we take a look at the group 16 hydrides, we have very asymmetrical molecules. There's only that one line of symmetry going down the center. So these are very likely polar molecules. And as a result, we're going to see dipole-dipole forces. Oops. Dipole, dipole, dipole. Be careful. Water is going to exhibit hydrogen bonding. We have an oxygen atom, which is a very small electronegative atom bonded to hydrogen. So we're going to see a super strong intermolecular force in hydrogen bonding, and water molecules are very attracted to one another. So let's get that first question. How are the plots between the group 14 and group 16 hydrides the same? Put it in green here. Yeah, if you look, the beginning of the graphs start off really similar, or I guess the end of the graphs, depending upon your perspective. When we're talking about everything from the 3rd period and down, it follows a really predictable pattern. We see as molar mass increases, so does boiling point. Next question is asking, how are the plots between the group 14 and group 16 hydrides different? Circle that in black. Well, the lowest molar mass molecule of each of those groups, the CH4 or methane and H2O water, they do not really follow the trend at all. Methane kind of falls in line with everything else that you see with the group 14 hydrides, but water has this unusually high boiling point. So the big difference between these two comes down to the lowest molar mass molecule for each of these groups. The next question is asking, if there were no IMFs, which is short for intermolecular forces, what would you expect the boiling point of water to be? Well, I don't have any numbers on this graph, but if we kind of just follow the trend that exists, you would expect it to be kind of close to methane's boiling point. Maybe a few degrees higher because it has a slightly larger molar mass. Water is 18 grams per mole. Methane is only 16 grams per mole. But yeah, if there are no intermolecular forces, you should see very similar boiling points, and there would be no liquid water on Earth as we know it, as methane is a gas at room temperature. Using what you know about intermolecular forces, what would you expect the boiling point plot to look like for the group 17 hydrides? So that's HF, HCl, HBr, and HI. Yeah, I'll let you think about kind of that one on your own, based on the intermolecular forces that exist and what's going to happen with your mass changing as you bond hydrogen to each of the halides. What would you expect to have happen? I'll let you kind of think about that one on your own. All right, the big takeaways from today's lesson are to know the 3 different intermolecular forces and understand the relationship between boiling point and strength of intermolecular force. It's a direct relationship. As intermolecular forces are stronger, boiling point tends to increase. As you can see at the bottom, you've got some practice problems. I know it's been a while since you've drawn Lewis structures, so probably a good idea to practice those. Predict polarity. We can use the symmetry shortcut, and then predict what sort of intermolecular force will be present. All right, thanks for tuning in, and I hope you found this video helpful.